Daily quiz for today. Do you have until? What time do you have until? 10:30. I'm sure I would be. We can just listen to one first. I'm trying to mention without me. All right, gonna lock answers here. I know it's not 10:03, but it looks like I have at least everyone in. So I'll lock answers in 10 seconds just in case you want to make a change. Locking in 5, 3, 2, 1. Locking answers now. And quickly, let's hear Brandon B. People, Kayla, you're on YouTube. Yeah. Aiden. Cool. It's gonna also help me remember names to know that one. Shunday. Emily. Vinton Charles. Biden, sorry. Thank you. Biden. Elijah. I saw him here. Michael. Maybe I'm miscounting. Oh, did Elijah come in and just. That's fine. Okay, got it. All right. So we're all good. What's the answer?
It's false.
It's all. So how do I make it true that these two statements are equivalent? It's an
The
and.
symbol should be and.
Yeah. So try to be a little tricky there. I gave you the symbol for what? Or. When logically it's really equivalent to where those two implications are joined with an and. Good job. All right. What questions y'all got for me before I get started? All right. From the iPad. Not the microphone. All right, so we're going to be moving on to chapter 2 of our textbook. We're going to start talking about some of the basic structures that we need for discrete math. When we talk about discrete, we're talking about discrete systems and discrete objects. So one of the first and most basic things that we use in mathematics, this is even in computer science, in discrete and outside of discrete mathematics is something called a set. Does anyone happen to know what a set is defined as?
Yeah, it's a group of elements.
Good. So it's not numbers. We don't ever restrict ourselves just to numbers. Group of elements, but does there have to be an order to it? Yeah, right. So we define a set as an unordered collection of objects. And those objects are often referred to as elements or members. So it's just an unordered collection of objects. We do have a notation with it because we're going to talk about membership of a set, where the set is going to be only elements. One server with I. Rather than having to write out every single time one is an element of the integers, right? We're going to have to use statements like that a lot, so we probably want a little bit more of a concise way to do so. Capital A. So we'll usually refer or reserve capital letters to represent sets. Unless there's going to be some special and lowercase letters to be elements if we were referring to a general element or a specific letter itself. Okay. You're going to see right here, a symbol A, that is a Greek epsilon that we're using there. And anytime we write something like this, what we're trying to say is little a elements of that set, which we just referred to as capital. Right, I gotta write 3 symbols versus 3 letters, really. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 3 versus 15, which would you rather write? 3. Kind of a common thing you like to have in there. Right? Am I still conveying the same thought? And that thought also be conveyed across multiple languages now that we understand the concept. Well, we love that. There's also a nice little trick to say if we want to, or if we wanted to note something is not in a set. And Lawrence, don't give it away. I know you know this. All right, everything else is not elements of the sets. Okay. What do you think I'm going to put here in between this little a, the element I'm trying to refer to, and the set A? Say that little a is not an element of the set A.
Is it all with a line through it?
Yeah, so that's the common trick that we always do in math. We want to negate the meaning of a symbol. We just put a nice little slash through it. So we're going to take that Greek epsilon. Let's draw a nice little line. That's how we're going to, if we need to, refer to specific element of a set. Now, when we talk about sets, we want to also be able to find ways to write out what the elements are. So let's say if I wanted to figure out supposed to be a cube for question. Let's see, how do we write the set of positive integers? Five. Well, there's not one absolutely correct way to write this set. There are multiple different ways, just as if you're trying to think in English language. If you have a concept, you want to state that concept to someone, there's multiple ways in which you convey your grammar, word choice, etc. Similar things can happen here. Not as many options, but there's at least two really common ones that you're going to see. First one is roster method. So what roster method just states is we're going to explicitly write out all the elements of the sets inside of curly braces. And we want to have those elements separated by comma. So if I was wanting to take that little question that we had, and say, okay, now I want to write out what does that set look like in the roster notation. Well, I'm going to need curly braces to denote the set. Do my best to actually draw them well. You'll probably see me kind of divert just squiggly lines by the end. So on. So starting with a nice little curly brace, and then what are the elements in the set? So all positive integers less than 5. List them off for me.
0, 1.
0 positive.
One,
So
one to 4.
2, 3, 4. Do I stop at 4?
Yes.
So less than 5. So just be 1, comma 2, comma 3, comma 4. I'm done listing everything in that set. Close off the set. Another curly brace. Kind of what you would probably naively want to do when you're trying to write out sets. Just write out everything that's in there. Well, that's not the only different way we can do roster method. Let's do say I want you to write out this set of all vowels, which we're going to call a capital V. How do I write this out in roster method? Oh, V is just the set, using that nice little curly brace. And what goes in there? What are our vowels, technically in the English language? A-E-I-O-U. What'd you say? Sorry. That's convenient. It don't have to just be numbers. Another example. What are the elements in this set? Smiley face on doesn't matter as long as I'm just separating all of my elements in that set by commas, and I'm making sure I satisfy it as an unordered collection of options. Yep. Now, I'm keeping it nice and simple right now. You think all, I mean, this is more coincidental. Examples I've given you, how many elements are in those sets? 4 or 5, right? Do you think sets are always going to be so small? So what if we wanted to say, hey, let's write set of the first 50 positive integers. Well, how do we do this?
You can still use Watson method and use the question.
Yeah. So we can always, as long as there's a clear pattern, that is a naive pattern, we put all that restriction to it, you can use what are called ellipses. With nice little 3 dots in a row. And I know I have a stopping point, right? 1, 2, 3, and I'm going to keep doing that pattern that I just established all the way up until what number? You can always use those ellipses. That is those little 3 dots. Whenever the pattern is simple / obvious in context. Just to make sure that we always want to satisfy that simple and obvious in context. So sets don't have any order to it, but I'm going to end up just because I like things to be ordered. I'm going to say, okay, I have a nice little order to how I'm listing the elements. They don't need to be there for set. I'm just putting it there. So if I follow this order that I've created in listing these elements, I'll use an ellipses there, right? Going to keep going on and on and on. What's the pattern? Will be the next 3. Yeah. Yeah, it's just the Fibonacci sequence. If you haven't seen it before, you're going to be going, what the heck is happening? If you have seen it before, or if I said this is a famous sequence, i.e. give you context a little bit, then you can probably figure it out. The answer would be 21, 34, and 55. Given the Fibonacci sequence, how do we find the next element in that sequence? At the previous 2 numbers. Start with 0, 1, 0 plus 1 gives 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 gives you 8, 8 plus 5 gives you 13. So now we got 21, 13 plus 8, 8, 13 plus 21, or 34 plus 21, 5, and I'll just keep doing that on together. Would you say that knowing that pattern was obvious? No, without context, right? So always be careful. Ellipses are something you can absolutely use. Always need to make sure that it is clear to the reader. what you're actually trying to do. So, okay, well, if we have these big sets, we can write ellipses to denote even an infinite set, right? There's no end to Fibonacci sequence. There are no ends or numbers in that set. Well, maybe is there a little bit more of a concise way that we can actually write these, i.e. another one? Right? I told you, just as if you want to convey a thought in the English language, there's multiple ways you can make statements to convey said thought. Same things here. Now, roster method's great if you have a very simple pattern or a very, very small set. Right? If you have a very, very large set, we want to actually think of a different way to write out how to say what elements are in such a set. We're going to talk about something called set builder notation. And you've seen set builder notation in your algebra classes. I'll show you where it actually came up. You have seen this before, but we're not going to be just sticking to real numbers. The set builder notation. How this works is within curly braces. We're going to characterize the elements. Of the sets by stating the property or properties they must have to be numbers. So what it's going to look like in general and have your curly braces still to denote that we're talking about a set. You're going to talk about your elements, what the members are going to kind of look like. Usually it's going to be just some variable, but you can also put an extra form in there. There's no specific thing that always has to be X or a letter A or a color blue. Don't really care. You do a vertical line. Anytime I'm seeing that vertical line, what I want you to translate in your head is the statement such that. And then following that, I need to state the properties or property that I need to have on those elements. So we can even just go back to some of those that we did. Sorry, one sec. Let's back. So what we did, set V. What do we call this before? The set of all what? Vowel. So set V can be all letters such that. The letter is a vowel. So the letter C be in the set. So we can say even B. B is not an element of that set B, but E is an element of that set. Another way to just note it. We could do Something like this set M. It's a little obvious, right? But what's in this set? So if I listed them out in roster method, the numbers 1 through 10, right? Integers 1 through 10. But yeah, X is just all elements that are positive integers. That's the day. 1, 2, 3, 4, 5, 8. And I guess technically none, because I didn't do less than or equal. I said less than 10. Okay. When we're dealing with sets that have, what we call finite elements, it kind of depends on the context and the situation, which one might be easier, roster method versus set builder notation. Right? But where set builder notation really comes into play and is most powerful is when we're dealing with very, very large set. There's so many elements in that set, you don't want to write them out, even if you potentially could. So, for example, especially when we have to deal with infinite sets, preferred. I guess I'm mixing up my statements when I'm saying what I'm trying to write. Set builder is preferred when dealing with extremely sets. This one I'm about to write here. I have a Q, you're going to see a nice little line on the left hand side of that Q. I'll explain where that's coming from in a little bit. Going to be the set of all elements of P over Q, such that P and Q are integers. U not being equal to 0. So what elements are in this set? Let's stop some things that will be in here. All I just need to think of, okay, what elements satisfy this condition? It needs to look like this, something over something, such that, well, P and Q are what? Integers with, you can just not 0. So I can pick any two integers, 0 over integer. So what's it here? Yeah. Something like, number 1 would be an element of this set. Number 2 is an element of this set. E1 over 5 would be an element of this set. Even -2 over 1001 would be an element. What is this really the setup? What did I just do? Not real. Fractions, which we call the set of what numbers? Larger than R. Rational numbers. This is just a set of rational numbers, and you automatically know, just from dealing with this a lot, how many rational numbers are there? More than a lot. An infinite number, right? But I'm able to write that out in roster method. Or even using ellipses, I could establish any pattern, right? So with set builder notation, I can tell you exactly what those elements are looking like. I'm covering all of that infinite number. Okay. That's really when set builder notation comes into, or really shines the best. And like I said, you've seen set builder notation before in your algebra days. Just one more example, and I'll ask for some questions. Got it. We go back to interval notation. How would you define this interval with these square brackets between A and B? I guess let me say different. The square bracket A comma B square bracket. Just describe what's in there. Everything between A and B, including. Well, you're probably actually given this in set builder notation when you first saw it. Probably ignored it because you didn't like the T in this, right? But it's a set of all x's such that is greater than or equal to A and less than or equal to B. We also have this, which is called an open interval. Instead of all numbers such that what? Just between A and B, not including A, not including B. So what does this look like in set builder notation? Well, instead of all x's, such that x is strictly greater than A and strictly less than B. And we had our other two cases. Partially open. These are all sets that you've seen before. Done in set builder notation. And technically, this is new. You just probably didn't want to remember it. So what questions I got from you so far? Anything like that? Right now, we're just talking about how we convey this finality in English language. We're just talking about how to properly construct a sentence. I'm not telling you how when you can use that sentence for, right? A lot of different things. We'll get into set and subsets, intersections, unions, and before we start the set operation. Right now, we're just making sure we get the basics covered. That set show up everywhere. So technically every. Let's see, who are my computer scientists? Ish. So if you have a term that is constantly being used, right, you're probably going to create a special name or a special variable for it, and you always refer to that variable from the rest of the system, right? Make it easier for you. That way you don't have to recreate it, rewrite it every single time. We have the same thing in mathematics for special sets. There are some sets that we just use so often, instead of having to write out necessarily the set builder notation, if even possible for them. We just want a nice little symbol to represent that set. So what is the most basic set of numbers that we can deal with in mathematics? Even less than that. So sometimes we're doing counting numbers. There's another name for it that we're going to use. the natural numbers. Integers are just all of your, you can say positive integers, technically, right, with 0. And then to get your negative integers, all you got to do is just the negative sign. So where did that set come from? Well, it came from the set of natural numbers, and we just tacked on more atoms. So we have the set of natural numbers. It's going to be denoted with an N. You're going to see I'm going to put a second little line. This is what we call chalkboard bold notation. So if you go look at the textbook for this course, and you go to like page 117, 116, somewhere in there, and you see where they define this. They use a bold capital N. And for the other sets we're going to do, they also have bold letters. So how can you write a bold A, a bold B, a bold C, and so on a white chalk? Shaded in, but that's annoying, right? It's going to waste a lot of ink, a lot of graphite on the pencil. So instead, we have this little chalkboard notation where we add in this extra line kind of somewhere. So you can see it confused before where I had rational numbers. That extra line, that's our way to know when we write it out, it's full. Okay. So you have the set of natural numbers, which is always going to be represented with that boldface N. And for us, following the textbook, and the S there is another way you can technically define the set of natural numbers, not giving 0. Some would argue that 0 is a basic concept, it is not natural. That's just a fun fact. For us, natural numbers 0, 1, 2, 3, 4, 5, 6, 7, and so on. Okay. After the natural numbers, what's the next step? Next set of numbers that a little bit larger, but not too much larger. That we see a lot. Technically already answered it. Right? So you have the set of integers. What letter do you think we're going to use for the set of integers? Why? Why would we do that? That doesn't make any sense. The most obvious choice is actually a Z. Really think about if you try to do boldface notation with an I on the chalkboard. I'm going to take my capital I and I want to add a line somewhere else. Where am I going to add it? Oh, wait, that's Roman numeral 2. Oh no, it's closure of set I. A lot of emphasis on the set I. Right? There's not really much very nice, easy way to do it. There's probably some other historical perspective that I don't really know. But we just use the set or the letter Z, the extra little line. So that's if I do it in roster method. 2, -1, 0, 1, 2, and so on. Now, another set that we're going to talk about a lot, and we've already referred to it even today, is a set of positive integers. This is going to differ from the set of natural numbers. Essentially going to be the set of natural numbers, but we don't include what else. Yeah, 0 is the answer. Natural numbers are 3 negative numbers. So I don't have to worry about any of the negative pieces. Difference is going to be set of positive integers does not include 0. What do you think we're going to use to denote the set of positive integers? Why? Actually, fun mess. But no. We're going to stick a little bit more obvious. We're still talking about integers, right? So what symbol am I still probably going to use? The Z. Yeah, the next little plus sign is. And then from there, if I technically want to talk about the set of negative integers, what would I probably do? Do the negative side, minus sign. Just give myself a little bit more space. All right, what's my next step up in the set of integers? Rational numbers. I start dividing those integers together. We saw we get the nice obvious choice of the capital Q. What helped me remember this before is when you find a set of rational numbers, Q is for quotient. We're introducing quotient. That's not saying why mathematicians chose Q. That's just what helped me remember. The set of all P over Q, such that we can even reduce what we have to write. P and Q are elements of the integers. With Q not equal to 0. That's how we define rational numbers. All right, from there, what's your next set of numbers? So irrational wouldn't be expanding on. It is irrational numbers are all the numbers in what set that are not rational. You combine the rational numbers and the irrational numbers to make what set of numbers? Real numbers. Our next major set that we deal with in mathematics, and that's pretty much what you stick with in all of, all of your algebra classes. Anyone have a guess what we use to denote for a set of real numbers? Part of the reason why we can't use it for the rationals. Old capital R. Again, we're throwing a nice little extra line in there. And that extra line is noting that it is technically what? Folded. Well, what I want to do if I want to denote the set of positive real numbers, or what would you assume? R plus. And then there's one more set of numbers that you have dealt with that goes beyond the real numbers. And remember what it is. It's when you bring in imaginary numbers. When you join imaginary numbers with real numbers, create the set of what numbers? Complex numbers. It's going to be a boldface C. I'm just going to put a nice little line inside of that C, denote that boldface. Remember, it's all elements of the form A plus BI, such that A and B are real numbers. So these symbols we'll be using a lot. I want to refer to real numbers, we use that R. Complex numbers, we use that C. Referring to the integers, I'm using what letter? Capital Z. All right, in the last 5 minutes I got today, we're not going to talk about set equality and subset yet. But one thing you want to be careful with sets. Go back to the definition. A set is an unordered collection of what? Objects. The set itself, an object.
Yes.
So, well, empty sets is another example, right? But a set is an object. So can you have a set inside of a set? Absolutely. You have to be careful when we're reading these things and trying to decipher. What that mean? A little bit more room. I'm going to call this my set A. And how many elements are in this set? Only 3 elements. What are the 3 elements in this set? Yeah, so 3 is an element of the set A. Okay, 2 is an element of the set A. And the set of positive integers is an element of the set A. Is 1 an element of this set? Not
Yes.
listed here. It's not. 1 is an element of the integers, but the integers is an object inside of this set. I'm only referring to the objects itself. Do I see 1 as an object in this set? Something like 1 is not an element of the set A. Negative 100 is not an element of that set A. This is one example. We can do another. Then define the set B. How many elements or objects are in this set? And just 4. What are those 4 elements of this set B? The real numbers, positive reals are elements. And when I say the positive reals, I'm not talking about the members of the positive reals. I'm talking about sets itself. The set of positive real numbers is an element of this set. The set of integers. The set of natural numbers. I'm referring to the sets. I'm not referring to the element of that set. This little method logic. Yeah, I kind of had a more interesting one. Yeah. This is what we'll end with. I have this set C. How many elements are in this set C? Only 3. What are the 3 elements in this set? And the set containing 1 and 2 is one of the objects in the set, one of the elements of the set. The set containing A and B is also there. And then triangle is also there. Is the element lowercase a an element of this set, capital C? No, it is not one of those 3 objects. It's not the set containing 1, 2. It's not the set containing A, B, and it's not the triangle. So A is not an element of this set, just like how 2 is not an element of that. So do we have class on Monday? No, the holidays. When's the next time I'm gonna see you?
Wednesday.
Wednesday. So next Wednesday, we're gonna talk about subsets, equality, maybe even get some other operations like intersection and so start using these sets. Okay? Otherwise, if you have questions for me, feel free to stick around and ask. I'll leave this up for a little bit. But I gotta get to my 11 o'clock class. Well, if you don't have any questions for me, have a good weekend. You too. See you. Yep,
Hi.
see ya.
You go back up to the set of the bachelor numbers.